Hello everyone and welcome to this class on attention slash transformers. How's it going, guys? Quick check. Am I audible? Is my screen readable? Awesome. 6387. So my screen is readable. Perfect. Cool. Hey, hi Arun. Glad you could join in, especially on a Friday night. So yeah, just one moment. I need to just take out some papers which I want to discuss. Yeah. Fridays are good for me to join. It's weekdays that are a bit hectic. Okay, I see. No, I mean, like, at least among my friends group, the mentality is Friday night is enjoyment, right? It's the beginning of the weekend and it's generally party mood. So, it's kind of impressive to me that people, despite having that mentality, like, people come and attend classes. That is amazing to me. Because even I feel like sometimes going out and all that, but yeah, it's okay. I mean, when you're doing a PhD, you don't really have such freedoms. So I learned how to deal with it. But yeah. Oh, okay. Remote working, so everything in Mysore shuts down by 8. Nice. Okay. That is good, right? Yeah. You can go to a location where you can't party. That is the best solution, I feel. Yeah. That way you're not obliged, like your friends won't keep troubling you. Why don't you come? Why don't that won't happen, right? That's good, yeah. Otherwise, I get a lot of emotional blackmail from my friends that I miss out on things. So, oh yeah, Snehal says your guide used to expect you to be present on Sunday too. Yeah, I totally understand. Like there were times when my guide used to call me up at like 2 or 3 at night. I used to be sleeping. I used to get up, see the message, and I used to rush to lab. Like there used to be these like for example we used to do deep learning, right? So there used to be server issues and I was quite good with Linux and figuring out how to fix those issues, so I used to be on call all the time. So if there was some training which has stopped it, I had to go monitor that, or if some lab machine had shut down, I had to put on the power and all that. So I totally get that. But it was fun. I mean, honestly speaking, that practice is what solidified my understanding in a lot of levels. I'm happy that it happened. See, like it is always a sacrifice, right? You give something, you get something. So I had to give my time and I had to, what I got was expertise in the sense that if something stops, I know how to get it working again. So I would rather have that expertise than, have parties. For me, that is the choice that I made. So it's okay. So yeah, because right now in the industry, at least that skill of mine is very appreciated. Like I got my internship at NeuroPixel because I was able to answer some questions at the implementation level. Hey, nothing like great and all. There are many people like this. Okay, Snehal, honestly. So yeah. Hey, anyway. I mean, I think almost all master students at IISc have that capability. Like they will know the code side also, they'll know the math side also. You should look at IISc undergraduates. They are amazing. I mean, I have never felt small till I went to a math class where the IISc undergraduates used to answer. It was an experience on its own. These people are like from a very young age trained to solve Olympiad level questions, and the sharpness that they have is next level. I mean, yeah. Anyway, sorry. Lot of reminiscing. Let's get back to topic. Okay. Sorry for the digression. Okay. So guys, today we're going to talk about attention and transformers. Essentially, what we're going to do is last class we had taken one small example of attention, right? Today we're going to try and understand how this fits into deep learning. So today is like a mixed lecture. So what I have done is I've taken the liberty to rearrange a certain portion of the way we usually teach things because I feel that makes more sense. So what we're going to focus on today is how do we take our RNN LSTM model? We'll figure out what are the issues with this model. We will see how attention fixes these issues. We'll talk about the end-to-end architecture of an LSTM plus attention model. Once we see all this, we'll go for code implementation. And finally, towards the end of the class, we'll talk about how transformers come into the play, right? So this is the broad plan for today. So what I'm going to do is I'm going to start the recap because to understand these things, right, we have to recap almost all the way from RNN lectures. So we need to recap some context, recap some information from almost all the lectures that we've seen so far. So we're going to try and do that. Okay. So let's do that. Okay. So first, let's first try and discuss the problem which we are trying to solve using all these techniques, right? The core problem is to capture the correct contextual information from a previously seen text and apply it correctly when needed. Okay. So two steps are there. First, you have to remember the correct information. Second is when required, you have to recall the correct information, right? So broadly speaking, all the approaches that we have seen so far, right? If you think about it, right? All the approaches that we have seen so far, RNNs, LSTMs, and GRUs, okay? They are very good at this part, capture correct contextual information from a previously seen text. They're excellent at this task, right? We have seen this. Why are they excellent at this task? Because we specifically set aside some memory locations. So for example, in RNNs, this is the hidden state. This hidden state's job is to encode information from previously seen text. In LSTMs, both CT and HT are doing this job, right? In GRUs, we have a single HT, but the way things are updated in this HT is controlled, right? As compared to an RNN, okay? So broadly speaking, capturing correct contextual information from previously seen text, RNNs, LSTMs, and GRUs are very, very good at this task. Do you guys agree or disagree? I'm going to pause here and I want your opinion. It's very important to go through these concepts step by step. Okay. So very good at this part, capturing correct contextual information from previously seen text. Okay. The hidden states are doing that. The main problem, okay, in my opinion, and in the opinion of a lot of NLP based researchers, so I've gone through a few survey papers. The general opinion is this, okay? The main problem with these models is that the recall is bad, okay? Encoding is perfect, recall is bad. It is not able to recall the right information at the right time to solve the problem, okay? And we're going to see examples of this and we're going to see why this is the case, okay? So what I'm trying to tell you guys is apply it correctly when needed. This is where these models are weak. Weakness of approaches that we have seen so far. Okay. This is the part where attention comes in and it fixes the problem. Okay. So at a very high level, what is attention giving us extra on top of whatever we have learned so far, right? Conceptually speaking, what attention is doing for us is it allows us to do the recall step very well. And today, our entire discussion is going to be on this part. Okay, cool. So 4 people agreed with me. There are 17 people in class. Just quick confirmation again, guys, because if you don't agree here, you will not follow the rest of the lecture. If possible, please hit the yes button if you have understood this. At a high level, attention's job is to fix the recall problem. If you have understood this, hit the yes button. Okay, fine. 6 people, 2 more people. Okay. I sincerely hope the others are also understanding this. Okay, let's move on. Cool. So we are going to come back and we're going to revise this attention mechanism a little later. Okay, I messed up the order of the slides. I just want to highlight this problem again. Okay, we've seen RNNs, we've seen LSTMs, we've seen gated recurrent units. All 3 of them are able to capture the correct contextual information and they're not able to recall properly. Let us debug this problem through an example we have already trained. Okay, so let's go here. Do you guys remember the funny results we were getting in the LSTM class? Do you guys remember this? I'll open this once more. Like some of them were really funny. Okay, let me just open this thing. I want to show you here itself what the problem is. Okay, we have already trained this model together. We've seen how that it gives funny results. We're going to now ask ourselves, where is this model going wrong? Okay, so let's kind of scroll down here. Let's look at some of the funny ones. Yeah, so this is where I have picked up two things from, right? Yeah, summarization. This the problem that we were studying in the LSTM class was that of summarization. What we had to do was we were reading a large bit of text, and our job was to summarize this, right? I want to now show you that encoding of information is proper, but recall is bad through these examples. These two specific examples we will see. Then we will go back to the examples we've seen here and we will confirm that this is the problem. Okay, let's do this. So first what I'm going to do is I'm going to read the review out. Okay, let me read the first review out. So first what I'm going to do is I'm going to read this one out. Okay, the review is Facebook has suspended a Canadian firm claiming it may be affiliated with Cambridge Analytica and improperly received its users' data. Okay. First sentence means Facebook was accessing a Canadian firm to get its data. It has suspended its work with that because they were supplying information to Cambridge Analytica. First of all, let me ask the audience, are you aware of the Cambridge Analytica scandal? Do you remember what this is? Okay. Few people are. Okay. Some people don't remember. I will give you my understanding. If I'm wrong, guys, please correct me. Okay. From what I understand, Cambridge Analytica was a firm which promised Donald Trump that, yeah, exactly. It's the Trump election scam. So Cambridge Analytica was a company, okay? They were like, we can use data analytics to get people, to get people elected. They were a company which claimed that we are going to use the power of data science and data analysis to put precedents on the chair, okay? And it turns out they were right. Yes, they were right. They used very specific targeted strategies to promote Donald Trump's image in the eyes of the public. Okay. So because Donald Trump he went to this company called Cambridge Analytica. He asked them, boss, get me elected. I'll give you how much ever money you want. You get me elected. Let's play with people's minds. So what these people started doing was they started analyzing the mentality of different people. They sort of tried to understand what would be, how to promote Donald Trump's image in this persona, in this persona, in this persona. So let us say there are 5 or 6 different types of people. They figured out for each of those types of people how to promote Donald Trump's image. Okay. And the scandal was this. Cambridge Analytica used data sources which were illegally obtained. Okay. Facebook, essentially Facebook's data, Facebook sells its data to different companies, right? That is how essentially Facebook makes its money. So what happened during Cambridge Analytica scam is the company Cambridge Analytica bought Facebook data from people so that they can understand and build a model on how those people think. And based on that data, they promoted Trump's image for them. Okay. So what is being said here in the first sentence is Facebook has suspended Canadian firm claiming it may be affiliated with Cambridge Analytica and improperly received its users' data. So the first sentence meaning is Facebook stops working with this Canadian company. What was the Canadian company doing? It was selling data which was not supposed to be sold for that purpose, right? The purpose of polarizing opinions. So that is the meaning of the first sentence. The second sentence is in response to Facebook's action, so here there is a missing term here. I think it is out of vocabulary. I think the name of this Canadian firm is there, but because we filtered it somehow, that name has gone. So just imagine that there is the name of that Canadian firm here. In response to Facebook's action, the Canadian firm said that it has never been and is not part of Cambridge Analytica. So once Facebook took this decision, Canadian firm says, no, we didn't sell them data. Okay, that's the second sentence. Third sentence is, earlier it was revealed that Cambridge Analytica exploited the data of Facebook users to meddle in the US elections. So this is the major problem, right? Quick question, is everyone clear on what this piece of text means? Okay, this is important, guys, because we are now trying to debug where is our LSTM going wrong. So I want to make sure the meaning is clear of this text. Okay, now let us see what the human written summary is, and then let us see where LSTMs fail. Human written summary is start. Facebook suspends Canadian firm amid data scandal probe. Okay, this is the human written summary. Does it correctly capture what is written in the article? Does it correctly do this? Okay, one person thinks it's correct. 2 people think it's correct. Okay, cool. Now let us see where our predicted summary screws up. Okay. Facebook suspend. So the first two words, if you notice, are proper. The major issue here is Facebook suspends something, right? So this part of the class, this part of the sentence is proper. Okay. Now here comes the confusion. What it was supposed to predict was Canadian firm. Okay. Instead, what it has put is Facebook. Okay. Can somebody help me understand where has this gone wrong at an analytical level, right? At an analytical level, where has this gone wrong? Can you first tell me Facebook and Canadian firm, are they sort of related entities? Facebook is also a firm. Perfect. Perfect. Right? They are related entities. Canadian firm and Facebook, they're companies, so their entities are related. So our vector representation of this is proper. Okay. Think of it this way. Our neural network is predicting the direction of the vector properly. It is not able to predict the magnitude properly, right? Why? Let us understand this. The word Facebook appears a lot more times than Canadian firm in this whole thing. Yeah. Not putting it in that order. Yes, Arun. I will agree with your explanation. Sort of like bag of words approach, but not putting it in the correct order, right? Why is this confusion happening? Because there is a lot of importance on the word Facebook here, right? So Facebook is there here, Facebook is there here, Facebook is there here. Okay. So instead of bringing the attention to Canadian firm, it has messed up and it has picked up the word Facebook from all of them, right? Do you agree or disagree? Agree or disagree, guys? Okay. So this is the issue, right? Instead of Facebook, instead of Canadian firm, it's picked up Facebook. So this is problem number one. So I'll label this as problem number one. We will list this down, all the problems down later. First, for this is problem number one. Okay. Now let's read the rest of the sentence. Amid data scandal probe. Okay. Amid data scandal probe and over fake news data scandal. Do you agree that these two are also matching? These two parts, the meaning, okay, the meaning of the words is the same, right? If you just lift these phrases up, okay, you will see that data scandal probe and fake news data scandal are very close in meaning, okay? So this particular summary of ours, LSTM, right? This has failed. Why? Because it was not able to correctly recall that it's the Canadian firm which has been suspended and not Facebook, right? Do you now understand why this model is making this mistake? It's making this mistake because Facebook is more emphasized throughout this text, okay? It has seen Facebook 3 times. It has seen Canadian firm only 1 time. So encoding is fine. The recall is the problem. It is not recalling, it is not putting the correct weightage on Canadian firm rather than Facebook, okay? Are you guys getting a feel for this? Is this feeling okay? Okay, cool. Guys, it's important to build intuition. Concepts can come later. Intuition is what will guide us. Okay, cool. So let's freeze this here. Now let's look at the second example. Okay, let's look at the second example. I'm going to read out the review again, and then we will discuss the results. Okay. The review is this. Siddaramaiah on Thursday accepted a 9-member committee's design for the proposed official state flag. Okay, so those of you who don't know, Karnataka has its own state flag. Okay, it's this yellow and red thing. So there is this red patch, and then there is this yellow patch below it, right? So this is Karnataka's official state flag. So this piece of news is talking about that event. Okay, so let's see this. Siddaramaiah on Thursday accepted a 9-member committee's design for the proposed official state flag. State flag here is of Karnataka. Okay. Siddaramaiah, for those who don't know, this guy is like a very famous Kannadiga politician. Okay. He comes from Lingayats and all that. Okay. Political season, so I'm getting a bit diverted. Let's not focus there. Let's come back. The committee was set up last year to examine the legal feasibility of an official state flag after demands by pro-Kannada activists. Okay. First sentence says Siddaramaiah has accepted the design. Second sentence is telling us a committee was set up to examine this legal feasibility, right? Oh, okay. Arun says red is below. My bad. Sorry, guys. Kannada flag is. I should be ashamed of being Kannadiga, honestly. The Kannada flag is yellow up, red below. Okay. Sorry for that. I knew I was making a mistake. I was just yeah. Thanks for correcting me. Okay, cool. Let's come back. Siddaramaiah on Thursday accepted a 9-member committee's design for the proposed official state flag. The committee was set up last year to examine the legal feasibility of an official state flag after demands by pro-Kannada activists. If the center approves the proposal, Karnataka will be the second state to have a separate flag after Jammu and Kashmir. Okay, so let's understand what's happening. Sentence 1 is telling us some chief minister has accepted a flag design. Sentence 2 is telling us a committee was set up last year to see if it's legally possible to have a state flag. And the third sentence is telling us apart from Karnataka, Jammu and Kashmir has its own state flag. Okay, now let us see what the human written summary is. Karnataka government unveils official state flag. Okay, this is the summary. Now I want to ask you guys something. Can I have made this summary without looking at the second and third sentence? Could I have made this summary without looking at second and third sentence? Okay, some people are saying no. Okay, I kind of disagree with you guys, right? Siddaramaiah on Thursday accepted a 9-member committee's design for the proposed official state flag, which means a state flag has been proposed and the design has been approved by the chief minister. Okay, let's get the meaning correct. Let's look at the second sentence. The committee was set up last year to examine legal feasibility. Karnataka. This is Karnataka, right? Oh, right. Okay. That's a nice. Okay. I cannot know which one without seeing the second sentence. Okay, that's interesting. Okay, fine. I will revise my previous statement. Is it possible for me to write this summary without looking at the last sentence? Can I write this summary without looking at the last sentence? Is there any information in the last sentence here that is coming in the summary? Not really, right? Okay, but I really like that argument, Arun. Yes, pro-Kannada. So Karnataka being the state is there, right? Okay, cool. So, okay, you require knowledge that Siddaramaiah is Karnataka's chief minister. So as a human, I would have been okay with the first sentence, but as a machine, I agree. I will have to see the second sentence. Okay, cool. Now, let us see. The summary is Karnataka government unveils official state flag. The predicted summary now is Karnataka government to launch. So this is why I have put it in brackets. Karnataka government, Karnataka GOVT. Both of these are correct. Okay. Unveils and to launch are also fine, right? They're close together in meaning. The major problem comes in the next part. Official state flag is what it should have said. New political entity is what it is saying, right? Can you guys tell me where is this information of new political entity coming in? Why was this confusion there? Do you agree that this confusion has come because of this part? The third sentence? So think of it this way. Why political entity is coming over here? If the center approves the proposal, Karnataka will be the second state to have a separate flag after Jammu and Kashmir. Yes. So political entity is a word or is a phrase which is associated with all the information over here. So if you think about it, because of the vector embeddings of this sentence, okay, because of the vector embeddings of this sentence, our RNN has screwed up, okay, because of these things. So if I had to debug this, I would say this problem is happening because it has focused on an unnecessary part of the sentence while doing the summary. Okay, cool. So first of all, do you guys agree with this? So let me summarize this. So this, I'll call this problem number 2. Okay, I'll call this problem number 2. Let us quickly note down what these problems are. Problem 1, so this is problems. Okay, problem 1 is this: loss of or forgetting information. Sorry, let me write problem 1 as forgetting necessary information. Okay, forgetting necessary information is problem number 1. Why is this the problem? Facebook appeared 3 times. Necessary information was Canadian firm. It forgot Canadian firm and encoded Facebook. Okay. The forget gate is not working as it's supposed to. Agreed or disagree? Do you agree that this is the problem over here? Quick yes. Okay, 2 people agree. Guys, 21 people in class. I honestly want you guys to be responsive because this is important stuff. You can get a job if you understand this properly, right? And at Scalar, we are committed to driving results. So it's important for me that you understand this. Okay, cool. Let's look at the second problem now. Second problem is that it is focusing on the wrong parts of the previously seen text, wrong focus on so focuses on the wrong parts of the text while generating summary. Okay, this is the second problem. It should have ignored the third sentence while writing the summary. That is what the human did. But because it has seen this sentence, it has forgotten other useful information and it has encoded new political entity here. Okay, these are the two issues with LSTMs. Okay, and this is the issue that we have seen for the text summarization problem. The same issues were observed in named entity recognition, in things like, in fact, no, named entity recognition, if you think about it, LSTMs are good, right? Sorry, not in named entity recognition. Apart from summarization, the same problem was witnessed in machine translation. So the first time people thought about these problems and thought about fixing it, right? It was in a paper by Yoshua Bengio. The problem he was trying to solve over there was machine translation. Okay, what is machine translation? I give you a text in English, you have to give me the text in Kannada, something like that. That is machine translation. Okay, the same problem exists in both these places. Why did we not encounter these problems in named entity recognition? Let's talk about that also, right? Why was this problem not there in NER? Guys, do you have to remember a lot of information for NER tagging? Or is only some part of the sentence okay? You don't have to, right? Exactly. You don't have to look at the whole text to solve the NER problem. You can focus on one sentence at a time. And yeah, right? You have to focus on one sentence at a time and you can get the named entities from there. So what I'm trying to tell you is, in tasks which requires you to focus on certain parts of the text, in tasks where you have to recall the correct information, that is where our LSTMs, GRUs and RNNs, all of these are failing. Okay. And today what we're going to learn is how is this attention mechanism going to fix these problems. Okay. Cool. So is everyone now clear on the context? I'll make one last repetition. Okay, one last repetition just for my sanity. RNNs, LSTMs, GRUs capture correct contextual information from previously seen text. The problem is recall. Okay. The problem is very correctly seen from things that we've already done. Okay. We can debug this from the things that went wrong in the summarization problem. Okay. Now comes the question. Okay, the solution is attention. The question is, how do we even apply this attention mechanism to solve this problem? Okay, that is what the rest of this class is going to discuss. Okay, cool. Now, before I talk about how to apply attention on your RNN, LSTM, GRUs, let us first quickly recollect the concept of attention from last class. Okay, concept of attention from last class. First of all, can I get a quick, if you need this recap, hit yes. If you don't want this recap, hit no. Okay, quite a few people need this recap. 3, 4, okay. Okay, it's close. Majority wins actually. So I'll have to recap this. Okay, let's go ahead and recap this properly. Okay, so many people need this recap. Let's do this. Okay, so let's recap the attention mechanism in last class. Once we recap this properly, we will go and see how to apply it to our LSTMs, GRUs, RNN architectures and fix this problem. And we're going to see that this works beautifully. The results that you're going to see today are actually quite good. So I'm kind of excited for that. Okay, let's move on. So now let's discuss this concept. Okay. First of all, what is attention? Attention mechanisms is a mathematical construct. What is this mathematical construct doing for us? It is allowing us to recall things correctly. Do you guys agree? Okay, actually, wait. I'll ask this question after I've done the recap. I'll ask this question after I've done the recap. So let's go through this first. Okay, cool. So the example that I had shown you last class was this one. Okay, we have a sentence which is food is good, but price is high. Okay, I want everyone to pay attention to two things. There are two major things which are being talked about in this sentence. The things which are being talked about in this sentence is food and price. Do you guys agree or disagree? Two major things are being talked about in the sentence, food and price. Agree? Okay, agree. Cool. Now, there are different sentiments associated with both these things. For food, the sentiment is positive. For price, the sentiment is negative, right? For price, the sentiment is negative. Okay. So we have one sentence now. There are two aspects over here. What do I mean by aspect? The noun on which something is being said, right? That is what I mean by aspect. So over here, I have food and price. Food sentiment is good. Price's sentiment is high. The question is this. I'm going to give this sentence to you. You have to tell me for this aspect, what is the sentiment? Okay. So the aspect that I'm giving you over here is this one. I'm saying cost. Can you tell me something about the cost given that this is the sentence? That is what I'm asking you to solve. Okay. Cool. So when I'm asking you about the cost, right, guys, do you have to focus on number 4 or do you have to focus on number 0? Which one do you have to focus? You have to focus on number 4, right? You have to focus on number 4. Okay. So we're in agreement on what we have to focus on. Okay. So now let us see how to build some math so that it is correctly able to focus there. Okay. Let's see this. So now this is what I'm going to do. This is my strategy. I'm first going to take this sentence and I'm going to convert it into vectors. How am I doing this? How do we take a sentence and convert it to vector? Word to vec, right? Word to vec. So the way we are doing it is we're going to take each and every word over here. Okay. So I have 7 words in this sentence. In this sentence, I'm going to take each and every word. I'm going to convert each individual word to a vector. And I'm going to gather these vectors together in the form of a matrix. Okay. For now, let us assume that the dimensionality of this vector is 5. Okay. And the number of words I have here is 7. So if I now take these 5-dimensional vectors, I put them on the columns. Okay. I put them on the columns and I have 7 such columns. The dimensionality of this matrix is what? What's the dimensionality of this matrix? Quickly. 5 cross 7. Perfect. So 5 cross 7 is the dimensionality of this example. In general, I like Arun's answer. It is number of words cross dimensionality. Sorry, it's the other way around, right, Arun? Here it is dimensionality cross number of words. So yeah. No worries. It's okay. Mistakes happen. We should enjoy those mistakes. Okay, cool. So this is my dimensionality. Now comes, how do I encode this query over here? Right? How do I encode this query? Can I apply the same process? I can take this query word, I can convert it to word to vec, and I can put that here, right? I can put that here. Okay, so this is what I'm going to do. I'm going to take this word, I'm going to apply the same word to vec. So now, again, the dimensionality of this is going to be 5. I have just one query word, so I'm going to call this a 5 cross 1 representation for the query word. Okay. Now, here is the challenge. This is what we want to happen. I now want to somehow emphasize price, okay, and I want to de-emphasize food. I want to de-emphasize food, okay. This is what I want to happen. I have given you the context that these are word to vec vectors. If I now take this 5 cross 1 vector and I calculate the inner product with each of these words, Okay, inner product with each of these words. Remember, inner product is like a similarity score. Okay, so out of all of these words, which word is cost most similar to? Yeah, Arun, you're right. But answer this question. Out of all of these words, which word is the word cost most similar to? It is number 4, right? It is price. So now, if I take this matrix and I take the inner product with this query vector, what I will get is a list of similarity scores, right? How many similarity scores will I get here? How many similarity scores? I'll get 7 values. Perfect, right? I will get 7 values over here. So each of these values now is going to be a 1, 2, 3, 4, 5, 6, 7, right? Each of these values is now going to tell you how similar is my word cost to these individual words, right? Okay. So this is what we have gotten here. So how am I getting this energy score? Inner product. Okay. So let me summarize these steps. If I have to build a summary for these 3 steps, I will say the job of the first 3 steps is to calculate similarity between text seen before and queries. Okay. Is everyone with me so far? This is important. Do you understand that this is what these 3 steps are doing? Okay, cool. Now let's move on. Once I have these similarity scores, I want to somehow use these scores to weight these words. Okay. Okay. So I have to now start thinking about these scores as weights. Can you guys tell me, do I have any control on the range of these weights if I'm doing inner products? Can the inner product be minus infinity? Can the inner product be plus infinity? What do you guys think? Can it be the case? It can be, right? They can theoretically be minus infinity. They can theoretically be plus infinity. Whenever I'm trying to weight something, it is very important for me to preserve energy over there. Otherwise, I will start encountering not a numbers, which is why this step 4 comes in. What step 4 is doing is it's simply going to take these weights. It's going to apply the softmax operation on this. And what I will get now is another vector, which is probability values P1, P2, P3, P4, P5, P6, P7. Why is this? Yeah, probability, so softmax. Exactly, Arun. So why am I doing this? Because I want to control the range of this. Okay, this can be minus infinity to infinity. So I'm going to, can't be inclusive. Yeah. Because this energy score can be anywhere from minus infinity to infinity, I have to encode them in terms of probabilities. Okay. Now, once I convert these energy scores to probabilities, this is what I'm calling my attention weight. Okay. Attention weight is something which is going to help me put focus on some words over here. Okay. Cool. So this is what step 4 is for. Now, let us look at the last part of this. So step 1 to step 4 is very straightforward. Now, let us see this part. Okay, let us see this part. Step 5 is get value vectors. Okay, value vectors is nothing but the text using which output should be generated. Okay, cool. So here is a quick question to you guys. I'm asking you something based on this sentence. So where will you take the knowledge from? Right? Where will you take the knowledge from? Will you not take the knowledge directly from this sentence? I'm asking you, what is the feedback with respect to cost? Okay. So where is this feedback with respect to cost encoded? Is it not encoded in this sentence only? Agreed or disagreed? It is encoded here only, right? Where will I find this information about cost? I will find the information about cost in the sentence itself. So now what I'm going to do is I'm going to say my value vector is nothing but my key vector here. Why? because the job I'm supposed to do is tell you something about the cost of this restaurant. Where is this encoded? This is encoded in my input sentence. So I will now treat the same sentence as my value. Okay, same sentence as my value. I'm going to apply these attention weights to these values only. Okay, cool. What is the advantage of doing this? Let us think about it. So before, every word in this key vector representation had the same weightage. Do you agree or disagree? Everything has the same weightage. But now, because of these probabilities, because of this energy score and attention weights, I'm giving importance to some words. I'm not giving importance to other words. Is everybody agreeing or disagreeing with this? Do you agree or disagree? Because of this step, I take this attention weight and multiply it with this value vector. I'm focusing on some words. I'm not focusing on the other words. How is my focus being controlled? My focus is being controlled by the similarity between this word and the query word, right? This is important, okay? Why are we doing all this? Because we want to get our models to focus somewhere. That focus is controlled by the similarity between my input and my query. Sorry, my input and my query. I drew it in the opposite direction. Yeah, input and my query. With all of this together, if I multiply this, the resulting weighted representation is what I call a context vector. Okay. So our final goal in attention is to build this context vector. How to use this context vector to solve our problem, we will worry about it later. Okay. The point is this. Okay. The point is this. Our RNNs, LSTMs, and GRUs were not able to recall properly. Why were they not able to recall properly? Because they were not paying attention on the right words. Okay, they're not paying attention on the right words. We have now found a mathematical way to ask this network to focus on the correct words over here when it is doing this job. Okay, and that is how we are going to use attention. Okay, cool. So I'm going to pause here and I'm going to ask everyone, do you understand what attention is? Do you understand the math? Do you understand why it's needed? Need feedback? Guys, if there is a no from anyone, please let me know. I will be happy to answer doubts here because this concept is important. If you forget these steps, right, we will not be able to apply it later. Okay, so these steps need to be clear. First, key a query, get similarity score. Once you have similarity score, convert it to probabilities and then reweight the input text so that it's easier to build a context. Okay. So in some sense, these steps are teaching my model where to focus on when it is doing its job. Okay. When it's doing its job. Cool. Okay. So if we have understood this now, if this query is clear, if this mechanism is clear, we'll now go and discuss how to do it for our models. Okay, cool. Before I go there, Azhar's question is, but the output will be price, right? How do we get the high? Okay, cool. So Azhar, that is where additional computation comes in here, right? Additional computation is required now. So here is the thing, right? If I give you this, don't you think the answer is obvious? I will not look at the highest weighted word. I will look at the second highest weighted word to answer. If I just give you the simple strategy, will you be able to execute it? Simple strategy, right? Whatever context vector I'm giving you, it will have the highest and second highest. You have to ignore the highest. You have to give me the second highest. Is this doable or not doable? Yes or no? This is doable, right? Okay. Let's go and check now if this high had the second highest weight. Let's see. Let's go back. I will go back to how we had calculated it last class. Okay. These are my, no, this is the context vector, right? What I want is the attention weights. Okay. These are my attention weights for each of these words. Okay. So the sentence is food is delicious, but price is high, right? Price is the highest weighted word. But if you pay attention, the second highest weighted word is high, right? So don't you think now the neural network can learn to do this? Ignore the highest weighted, take the second highest, right? Our neural networks are function encoding machines. They can learn how to do anything. So now the neural network will learn from data that I shouldn't give the highest rated word, but the second highest rated word, right? Is this happening or no? Cool. So this is how our neural network will learn to solve this. This is why we will keep trainable components at the end of this. So this exact mechanism we're going to discuss. Just give me some time. I'll come there. I just want to make sure everyone is okay with this. Okay. Any doubts here, guys? Now is the time. I want to proceed. So just, okay, no doubts? Fine. Let's move on. Let's move on. Okay, cool. So let's see where we are. We know now that our networks are capturing correct information. We know now the problem is not able to focus. We are saying, let's use attention. Question is how to use attention. Now let's answer that question. How am I going to use attention to fix this problem with RNNs, LSTMs, and GRUs? This is the question we are going to answer now. Okay. Quick look at what is going to come next. Different types of attention mechanisms. Once we know how to fix it, we'll go and see what are the other things we can do. Then we will see this in action. And then I'm going to slowly introduce transformers concept. We will do detailed discussion of transformers next class, right? The good thing is attention and transformers are very interlinked concepts. So it will not feel like a rough journey. Okay. That is my promise to you. If it does feel like it though, please correct me. Okay. It's important now that you give me feedback. Okay, cool. Okay. So now let's come to our architecture and let us see the problems and let us see how to apply attention to fix this. Okay. First, quick check with everyone. Have I written the correct steps over here? Have I made a mistake in the steps? If I made a mistake in the steps, point it out. Are these steps correct? I'm now testing your memory. Okay. Are these steps correct? This is step 1. This is step 2. This is step 3. This is step 4. This is step 5. This is step 6. Okay. Indradeep says I've missed out. Stop max. How am I getting attention weights from energy score, Indradeep? By softmax, no? By softmax. Let's go back. Let's go back once. See, softmax is used to convert an energy score to attention weight. So that is there. That's not a problem, right? That's not a problem. Okay. So now that you guys have seen both slides, quick confirmation. Are these steps correct? 1 to 6. Okay. 5 people are paying attention. 6 people are paying attention. You're saying steps are correct. Perfect. Okay. Now what we're going to do is we're going to see what to bring from this architecture, what to take from here and put it here so that our issue is solved. That is what we're going to do. That is what we're going to do now. And guys, I need a lot of focus here. Okay. If you understand this, trust me, you will find a lot of future things easy. Okay. So please lend me your attention for the next half an hour at least. Does anyone want a break at this point? If you want a break, say hit a yes. Otherwise, hit a no. Okay. Okay. Not many people want a break. Concept is fresh. So let's discuss it right away. Okay. Let's do that. Let's do that, guys. Perfect. Cool. Now let's come here. First, let us quickly recap what we mean by encoder-decoder architecture. First, let's focus on that. Once we understand that, we will come back and see what the problem is. Remember, what is the problem? Our network is not recalling properly. Let us debug this issue in this architecture. Okay, let's see how the encoder works. Okay, let's take our sentence, example sentence again, and let's see how we will pass it through this. So food is good, but price is high. Okay. If I take this sentence and I pass it to this RNN, can you guys quickly tell me how many hidden states will be generated? Okay. One hidden state, really, Arun? 7. Yeah, 7 hidden states, right? I will have one hidden state for food. I will have one hidden state for is, one hidden state for good, and so on. Okay. Final output is 1. Yes, yes, yes. I agree, Arun. I'm coming there. It's like, Arun, you're answering 2 questions ahead. Please stay back, right? I know you're understanding this well, but hold on. Okay, cool. So now let us see. Food is good, but price is high. I will get 7 hidden states. Now, here is what Arun is telling us, guys. Arun is telling us, fine, we have generated 7 hidden states, but the decoder is only going to see the final state. Only one state is going to go from here to here. Okay. Is this a problem? Do you think this is a problem for the recall? Is this a problem for recall? Yes. One person says, two people say yes. Okay. Four people say yes now. Okay. Five people say yes. Cool, cool, cool. Enough people are saying yes. This is an issue for recall. I'm generating 7 states, but I'm only passing 1 state. So it is the job of this hidden state to encode the information of all 7 words. So a lot of pressure on this guy. Think of it. It's like everyone did something, but this guy has to deliver, right? So the last person usually in a team has to give the final result. So in some sense, this is the guy with the most pressure. Okay, the dependency is in this guy, and of course, under pressure, nobody is able to do well, right? So we have to help this guy do better. So one fix is already available to us. Okay, one fix is already available to us. What is that fix? Maybe try passing all hidden states forward. Okay, maybe try giving all hidden states forward. Yeah. So Arun's in private chat, Arun says, is it like we get intermediate encodings and apply attention on decoder? Yes, yes, Arun, you're on the right track. You're on the right track. Keshav's question is, encoder decoder architecture is independent of mechanism used. Am I getting correct? Yes. Encoder decoder architecture is always like this, Keshav. I have to use the same architecture for NER. I have to use the same architecture for the other thing. Now, what was that? Summarization. I have to apply the same thing for machine translation. All of these encoder decoder architecture remains the same. Okay, that's what. Okay. Now let's move on. This is the problem with the encoder. We have figured out one bottleneck. The final encoder hidden state has the responsibility of encoding everything. This is not doing its job properly. So one fix is maybe we can try giving all the information. Now let's see the decoder side of things. Okay, the decoder side of things, what is happening is it's getting this final encoded state. Okay, then it is using this encoded state to generate the output, right? Okay, so now my question to you is, at the time of giving the final answer, right, what all information is available to this OT? What all information is available to this OT? Let us see. The information available to this OT is this final state. The information available to the OT is the hidden state of that is getting generated at the decoder architecture. Okay, these are the two things that it sees. Agree or disagree? For every output, it's using two things to get the output. It is using the hidden state and it is using the current weights, right? Current weights of this. Agree or disagree? To generate this output, the only thing it's seeing is the hidden state and whatever computation is being done here. 3 people agree. I'll wait for the other people to agree. Okay, more people are agreeing now. Awesome. Okay, so 3 more people have agreed. OT is also input, right? Indradeep, in some cases, yes, OT is also there. So in some sense, yes, it is seeing the previous output also. Okay, so this guy is seeing 3 things. Sorry guys, I'll revise my statement. It is seeing 3 things. It is seeing the hidden state of the previous state. It is seeing whatever computation is happening here. And the computation is happening even on the output that was generated on the previous step. Okay, so 3 things it is seeing: hidden state, computation, and output. Okay, this is what it's seeing. Now, let's understand something here. When this output is being generated, right, is there any way for me to feed in the information of the aspect at this stage? Is there any way for me to do this right now? So let us say I gave you this and I asked you for cost. Okay. Is there anything in my LSTM architecture already which can focus on a word which was occurring before? Yes or no? No, right? And that's the problem. That is exactly the problem. When it is generating this line or this word, it has no direct access to the previous words it has remembered, right? It does not have that access. So maybe also try passing info of the input word. See, there is a difference. There is a hidden state with the word. There is the input word itself. Okay. And that is where I'm asking you to focus. The first issue is with the hidden state. The second issue is with the word. Okay. The second issue is with the word. Maybe also trying passing info of the input word. Okay. This is what Anil says, but in LSTM, we had cell for long term to handle this, right? Yes, Anil. We had that cell to handle this, but we just saw, right? In all our discussion, we saw that even though we have this CT, it is still making these mistakes. Even so basically we intended for that long-term memory to work in some way, but it is not working as we are expecting. So that is why we have to fix this problem, right? See, we solved the problem with our best intentions. It didn't work. So we have to learn from that and improve it. That's simple. So what is the problem even with that hidden state? Forgetting necessary information focuses on wrong parts of the text while generating summary. So it is not focusing on the right things, right? So now the question is, how do I fix this? The answer is attention. Question is how? That is what we're trying to figure out here. Okay. That is what we're trying to figure out here. Okay. So we have debugged the issues on this architecture now. We have debugged the issues on the architecture. Now we have to think of implementing these steps within our attention mechanism. Okay. Let's see how to do this. What I'm going to do, guys, is first I'm going to give you the answer. Then we're going to discuss it. I want to first get the answer out of the way. I don't want people to think too much on this. Otherwise, we'll go into weird directions. I want to first give you the answer. Then we will discuss why this works. Okay, we'll discuss why this works. So the answer is this. I am now going to take, so now I'm going to focus on part one. Okay, I'm focusing on this part. I'm going to take all these hidden states which are getting generated. Okay, not just the final one, but all of them. I'm taking all of them and I'm going to call this as my key vector. Hidden states from encoder. Okay, hidden states from encoder is what I'm now calling my key vectors. What is my query vectors? Don't you think query vectors should come from what is important at this stage? Like the question of what word to use next is coming at decoder time, right? Key vectors are like what I have to remember. Query vectors is what is needed right now. Okay. So the correct answer for what should the query vectors be is I'm going to use the hidden states from the output side. I'm going to use the hidden states from the output side as my query vectors. So let's note this down. Hidden states from decoder. So let's talk about why this makes sense. First of all, what is the issue here? I'm not able to recollect the correct information when I'm generating my next word. Why is this a problem? Because first, I don't have access to my previous hidden states. Second, because I don't know which part to focus on, right? So the query vector is nothing but the previous hidden state. I have already generated something. What should I generate next? That question should be answered by what is missing in this, right? So to some sense, to some extent, my query vector should be based on what I already know and what I should give next. And my key vector from where I'm getting my information is the input hidden state. Okay. So that is why when I'm going to use attention to fix the problem of my LSTM, okay, I'm going to give hidden states as my key vectors. My hidden states from decoder is query vectors. Okay, Arun, I'll repeat this once more. First of all, guys, let's go back. Let's recollect this from here. What's the job of the key vector? The key vector's job is to store information which is useful. The job of the query vector is to ask what is the relevant information from that here, right? Do you agree with this, Arun? The job of the key vector is to store information. Job of the query vector is to ask what is important here. So the hidden states from the encoder are what is storing the relevant information. The hidden states from the decoder is like a question. What am I missing for the next output? Right? Think of it this way. My RNN at this stage has already generated one output. There is something which it has to generate next. So now I'm asking you, What should I generate next? The importance for that, the query for that comes from the hidden states of this RNA, right? So my key vectors now are going to be hidden vectors, hidden states from encoder. My query vectors are going to be hidden states from decoder. I want everyone in class to say yes if they understood this part. Again, very important, guys. Have you followed it till here? Why am I giving hidden states from this as query? Why this is key? Okay, cool. Okay, awesome. So now let us go and see the next few parts. Now we have to get some similarity or dissimilarity, one of these two, okay? We don't, so now it's, think of it this way. We have freedom to capture similarity also and dissimilarity also, okay? If I use inner product, am I forcing myself to capture similarity? Am I forcing myself to capture similarity? Does the inner product always give me similarity or does it give me dissimilarity also? What do you think? What happens when dissimilarity is there? Don't you think the inner product goes negative? Don't you think it goes negative? Think of it this way, na? Yeah, low value. No, not low value, Azhar. It goes negative high value. Think of it this way. I have a vector here which is man. Okay. Don't you think logically speaking, woman should be here? Equal energy, opposite direction. Okay. Think of it that way. So my inner product, okay, my inner product is capable enough of capturing both similarity and dissimilarity. If it is dissimilar, you have to emphasize the negative part. If it is similar, you have to emphasize the positive part. Okay. So the energy score, I'm still going to keep the inner product over here. Okay. For now, we're still going to use inner product. After we have this concept, clear, we're going to go back and see what else we can do here. Okay. But for now, I just want you to think of this as inner product. Okay. Let's do it that way. Fine. Now, we have to get attention weights from this. Do I have to change anything? Softmax is good enough, right? Softmax will always take a vector, give me probabilities. Any changes required here? No, right? Okay, cool. So softmax is good enough here. Let me note down softmax over here. Okay, cool. Now, here is the fun part. What are my value vectors? How do I get this context vector? How do I use this context vector? Let's answer these questions. Okay, let's do this. Can you guys just give me 1 second? I just want to confirm the math once. Once I have the math clear, I can explain. So just 1 moment. So Yj is this. Cool, right? Okay. Okay, awesome. So now let's answer this question. Okay. So before I go there, Anil's question is, can cosine similarity be used for energy score? Yes, Anil. It's one of the other options that we have. For now, let's just use inner product. Why am I focusing on inner product? Because the first paper used inner product. So I'm just going with that. We will see other papers and variations and why later on. For now, I just want to use this and move on. Okay, that's all. So let's discuss that part later. For now, let's focus on this. Okay, let's go back once and see. What is the job of this value vector? The value vector is basically the text from where I should give my answer, right? The text from where I should give my answer. Let us focus on this aspect-based sentiment analysis problem. Don't you think I have to use the same text again? Don't you think I have to use the same text again from where I should retrieve information? Okay. So then what do you think should be the key value vectors? What do you think should this be based on this? What should this be, guys? Very simple, right? No. Arun, not X. See, what did we do previously? Whatever was the key vector, that only we used as value vector, right? Same thing. We did not go back to the word encoding. We stayed with that. So can I say that this is also hidden states from encoder? Can I say this? Okay. Nice. I like Keshav's answer, Keshav's question. Keshav, I'll come back to you, right? I'll come back to you. Cool. So hidden states from the encoder is what we're going to pass as our values. Why? Because our knowledge base, the place where we've stored this relevant information, is in these hidden states. That is our firm belief, right? So that is why this is also what we're going to keep as value vectors. Okay, cool. Now, if I simply multiply the softmax weights with these hidden states from encoder, I'm going to finally build my context vector. Okay. So think of this final context vector as a linear combination of all of these hidden states. What do I mean by linear combination? It's this, right? I will take this, I will multiply it by some weight, and I will add these vectors up. That is what I mean by linear combination. So my context vector now is a linear combination of all the hidden states, and our hope is that the attention weights are now putting the right weightage on the right words in the sentence. This is what our hope is, right? This is what our hope is. Now comes the question. I have painstakingly created this context vector, right? I have painstakingly created this context vector. How do I now use this context vector to do further computation, right? That is the final step. And this answer is what will answer the second part of this question, okay? Maybe also try passing info of the input word to this, right? Okay. So we're now going to see how to make use of this context vector to give the final output, okay? So here is the major change, guys. Before, my output was being given simply by, so think of it this way. Okay, let me actually write it explicitly and then explain it, right? Okay. So before attention, RNN math. Okay. So before attention, we will see what we were doing. After attention, we will see what we are doing. Okay. Okay, cool. Now, this is RNN math, guys. Please don't get confused. I'm not writing the LSTM version here. I'm writing the RNN version. Okay. You could get confused if you think about the LSTM. I'm again repeating. Think of the RNN, not the LSTM. In RNN, did we have just one hidden state or two hidden states? First, tell me that. One hidden state, two hidden states. One, right? RNN has one hidden state. Now, let us go back and see what the RNN math was. In RNNs, the final output, right? It was basically a function of the following. It was a function of the previous hidden state, right? It was a function of the previous output, right? And that's all. That's all. Whatever else is up there. So all the trainable parameters, the W, the B's, all that is inside this function, okay? So previously, our final output was being determined by two things, HT-1 and OT-1, okay? RNN math, not the LSTM math. Now, the question comes, how should I use this new context vector, right? How should I use this new context vector? So this is what we're going to do after attention. This new context vector that we have so painstakingly created, first let me give it a name. I'm going to give the name to this as CT. Okay, this context vector that we have created after doing all these steps, I'm going to call it CT. I'm going to take this CT and I'm going to generate my output by using this CT as well, right? So my final output now, my final output is not only going to be a function of the previous hidden state. So again, let me remind you, this is the encoder's previous hidden state. The decoder's hidden state, decoder's previous hidden state. This is output T-1. This is decoder's previous hidden state and output T-1. And in addition, I'm going to give it one new thing now, which is the context vector. Where this guy, context vector from attention block. Okay, this is the context vector from the attention block, right? So I'm going to now finally get my output using the previous decoder hidden state, the previous output, as well as this new context vector. Okay. So these three things now I'm going to use to generate this final output after attention. Before attention, I was just doing this. Can you guys quickly tell me why is this, why this will give me an, uh, why this will give me an advantage? Do you agree now, because of this new context vector, we have a way of capturing only the relevant information for generating the answer? Do you agree or disagree? Two people agree, four people agree. Okay. Guys, if anyone is confused or doesn't agree, please say no, right? Again, it's important for me that you understand. The other party is okay. Okay. Arun's question is which to focus and which to shortlist in priority. Yes, both of those things are being captured by this context vector. Why? Because of the attention weights and because of this energy score. These two important steps are making sure that my context vector knows where to focus and which to prioritize. Okay. So one moment, I got a question in private chat. On the decoder side, we will be able to capture mostly the same words in the input. Yes, yes, absolutely. You're right. But Keshav, don't you think we have a choice here? If I change my value vectors here, I can control that also, right? Think of it. I can control it. So beautiful thought. It's a beautiful thought. That's a good observation. Whatever we're getting here, we're getting using the same words from the input, but I'm totally free. See, that is what, when we change our application, right, the way we will set this key vector, query vector, and this value vector, all of these are going to change. I'm right now just looking at aspect-based focused attention, aspect-based sentiment analysis. I'm focusing on that problem. So for different problems, like ChatGPT will do this totally differently. Okay. So when we come to BERT, when we come to generative models, we will see how these change. But for today, I want you guys to be clear that this is how we're doing it. Okay. So let's worry about that stuff later. Okay. Cool. So now I have answered the question. Okay. After all this discussion, I have answered one very important question. How to use attention to fix the problems with RNN, LSTM, GRUs. How am I doing it? I'm doing it by putting the hidden states from encoder as my keys, the hidden states from decoder as my queries, the energy score I'm going to fix as inner product for now. Attention weights, I'm only going to use softmax. Value vectors, I'm giving the same thing that I gave as my key. Okay. And finally, this is what I'm going to give here, right? Okay, cool. So this is essentially how I'm solving this problem. Fine. Okay, now let's move on, right? Let's move on. Let's, sorry, go back. I need to see what, So if we have understood all of this, right, guys, what we are going to next discuss is what all can we change here and why, okay? I want to give you guys a break here. This is a logical point for a break. I want to give you guys a break here because I want you to remember these parts well. Okay, I want you to remember this part well. Uh, what I'm going to do is I'm going to leave this on the screen here. I'm going to set a 5-minute timer. Okay, and we're going to come back after 5 minutes and see what are the different changes we can make to this pipeline and why it would be a good idea to make that change. Right? Okay. So that is what we will do. Is everyone okay with this? Is this a good time for a break? Okay, 3 people agree. I hope the rest of the people also agree. Okay, so let's do this. I'm going to start the break time now. And once we come back, we will take this pipeline, we will start making changes to it, and we'll see why we have to make that. Okay, see you guys in 5 minutes. And we're back. Are we back? Okay. One person, two people are back. Three people, four people. Nice. Okay. More. Okay. More people are coming back. Okay. Happy. Cool. So let's resume here. Before I resume, I read this amazing comment by Keshav. I'll just read it out. Keshav says, for machine translation, we can have key in one language, value in another. Okay, I agree. Uh, um, does this is this actually how it happens? We will see. Okay, Keshav. I don't think this is actually how it happens, but I appreciate the thought. It makes sense to have value vectors in machine translation to be things of a different language, right? It makes sense, but for machine translation, at least I can tell you, our intention is both the word in this language and that language should relate to the same hidden state. Okay, so for machine translation, I kind of disagree. The value vectors still have to be the hidden states. Our hope is we will teach our network how to take one concept, which is a vector, and learn how to translate it from one English word to this one. Okay. So slightly disagree there, but I appreciate the thought. Maybe you can apply your idea to improve performance. It's possible, but the way I have seen it happen, mostly what people do is they use the same thing. Okay. Okay. Next one, for question answering, we can have key as each sentence and value as question, I guess. Yes, this is actually correct. Okay, so for question answering type of problems, there is something which is known as hierarchical attention. And I want to point that out in our discussion now. So just wait, I'll get there. And but your guess is correct here. And only key value vector should be changed. Yes. Actually, we have to do something slightly at the query part as well. So that slight change is there in hierarchical attention, but we'll come there. But really appreciate the thought. Okay, cool. Now let me take Arun's question. How to match the key to query? How to match the key to query? We're using the energy score now, Arun. The similarity between key and query is being captured by these two things, energy score and attention. And Arun, oh, sorry, there's a follow-up question. Like, how can English key relate to Kannada query? This is good. Okay. So, Arun, our hope is this. Our hope is this. The same hidden state will go to an English word as well as a Kannada word. We want to build our RNN in a way that the same hidden state encodes the English word also and the Kannada word also. And depending on how you're doing the decoding, that will change. So the conversion of this hidden state to English, the conversion of this hidden state to Kannada, that is being taken care of by the RNN. Okay? That is being taken care of by the RNN. That is why we have a deep learning system sitting there. We hope that the network will learn to do that. And in fact, I will prove to you that that is what happens. I have visualizations which will prove that the network we train ends up doing this only. Okay, so we'll see that. Cool. Any further questions? Otherwise, I will continue. Guys, is the pace okay so far, or am I going fast? If it's okay, hit a yes. I just want to make sure I'm not going too fast. Right? Okay. Pace is okay so far. Perfect. Let's move on. If you think the pace is not okay, guys, remember you can always ask me questions. Right? Okay. Fine. So let's move on now. Now we're going to discuss how to take this attention pipeline and change things. What can we do to make things better here? We're going to study each and every individual part over here. Okay. Okay. So now let's break this down into something. Whenever you're designing an attention mechanism, right? What are the things that we have to keep in mind? Let's think about that. First thing that we have to keep in mind is how to specify key, query, and value. Okay. So let's note this down. Designing attention mechanisms. Question 1 is how to set key, query, value. The answer to this question is highly dependent on what? What do you think this should be? Fill in the blanks, guys. I'm testing your RNN now. Fill in the blanks here. Highly depends on the use case. Use case or the task that we are performing. Perfect. Everyone's RNNs are working properly. Cool. At least Anil's is. I didn't get responses from other people. I can say Anil's RNN is perfect. Okay. Second question. Okay. So we have taken care of three things here, right? Key, query, value. What else is remaining? How to set the energy score and attention weights, right? Let's use that as question 2. How to generate energy score and attention weights. Right? This is the second question. The answer is choose one of many options. So what are these options? We're going to discuss now. Question 3, the final question here is, okay, we have taken these attention weights. We already have decided what our value vector is. We've generated a context vector. How to use this context vector? That is the final question, right? Final question, how to use context vector. Any guesses? The answer is obvious for this one also. Any guesses what the answer is? Shouldn't this be the same as answer to question 1? How to use this context depends on the use case, depends on the task, right? So I'm simply going to copy the answer to question 1 and paste it here. That's all. Okay, wait, the answers are not aligning. I'll just copy the answer part. Yeah. So this is what, okay, cool. So now let's go and understand this important question. Okay, this is what we're going to discuss next. So let's go. For this, I'll have to come back to our notebook, a very nice notebook. It has a lot of useful information. Let's go through this now. Okay, fine. So remember what we're answering right now is question 2, how to generate energy score and attention weights. Another name for this energy score, right, is alignment function. Why is it alignment function, guys? We're going to discuss in detail next class. Okay. But for now, I just want you to remember whenever I'm saying alignment function, it is the same as the function which I'm using to generate the energy score, right? Okay, that is what. Before I move on, Keshav has a question. What will go wrong if you use attention in all NLP tasks? I don't see any downside apart from overfitting. Keshav, hundreds of researchers over the last 4 to 5 years have proven that you're right. Okay, there are hundreds of papers which show that attention is so useful that it improves all NLP tasks. Nothing is preventing us except for ignorance. Maybe the only reason why we won't be able to use it right now is we don't know how. So that is what we're doing, right? We're fixing that problem. We're learning how now. So that's what. So let's learn how to do it properly, and then we'll go and see if it helps everywhere. But I have read a few survey papers which show that attention actually does improve most NLP tasks. The places where it does not improve, right? I'll give you a hint. If I don't have to recollect from a large body of text, right? LSTM with some other LSTM plus CRF and attention both will have similar performance, right? Have we seen this in NER? Keshav, last class? Did we see this? We saw that, right? LSTM plus CRF has comparable performance to a transformer. So that's what. Where attention shines is when we have to take information from large texts. That is where it shines. Okay. Okay. Now let's move on. What are the different types of alignment or energy functions? So now the question I'm trying to answer is how to generate this energy score, what all can we do, and which one to choose for what task. Let's discuss this now. So broadly speaking, there are 4 different types. Okay, there is similarity based, there is general, there is additive, and there is location based. So let's go through this one at a time. Okay, let's go through this one at a time. So similarity based alignment functions or energy scores are these things. Similarity such as cosine similarity, this is one option. Dot product is another option. Dot product is the only one we have taken so far. Then we have the scale dot product. Okay, let me explain the scale dot product for a second. Okay, so let us see the forms of these functions. So similarity is nothing but sim of q comma k, where q is your query vector, k is your key vector, right? So cosine similarity is kind of straightforward. We know it's the angle between these two vectors. Okay. Dot product is also straightforward. We know how to calculate dot product. Now, question is, what is the scale dot product? Why are we putting this underscore n in the denominator? So first, let me tell you what this underscore n is. Underscore n is the length of these vectors. Okay, it's the length of these vectors. Now, my question to you guys is, why do I have to divide by this? Any particular reason? Does it have anything to do with the size of these representations? Will I be biasing? Yes, it is scaling, Indradeep. But what bias is there in my inner product that my scale dot product is solving? What is that bias? That is the question here. Major question is, why am I doing this underscore n? What is the advantage I'm getting? The advantage is this, guys. Usually, larger vectors will mean better contextual information, right? More memory, more representation. Do you agree with this? Agree or disagree? If my hidden state is larger, then I'm capturing more information, right? But then the issue there is in high dimensional spaces, right? When you take inner products, you have an inherent bias on the weight of the inner product by the dimensionality. So if you take two small vectors, calculate the inner products, you take two large vectors and you calculate the inner products. If the inner product is 1, it means something else for two-dimensional vectors. It means something else for high-dimensional vectors, right? This inherent problem I can explain mathematically, but I don't want to go into the depth of. Okay, take it from me that this will have different meaning. A 2-length inner product and an 8-length inner product will have different meanings for that number 1. Okay, so what mathematicians found out is if you divide by this root of the size, right, it brings the representation power to the same range. Yes, kind of like TSNE concept. Yes. Perfect. That's a good relationship. I didn't think of it that way. That in TSNE you basically make sure everything is in the T distribution, right? Same idea here. So basically now I have to take the underscore over here to fix the inherent bias with this dot product. Okay, cool. So these are the three options if I'm using a similarity based alignment function. Okay. Now, guys, can you tell me, out of all of these three that we have discussed, is there any scope of learning anything here? Do we have any learnable parameters in this? Yes or no? No, right? We don't have any learnable parameters. Yeah. Oh, Arun, yes, I agree with that. Relative neighborhood rather than magnitude neighborhood. Yes, I agree with that. So for now, let's focus here though. There are no learnable parameters here. I cannot adjust this at runtime, right? At training time, I'm not able to adjust this. What if some other measure worked better than inner product, right? What if something else worked better? To fix that problem, we have something which is known as a general alignment function, okay? The job of this general alignment function is to add some parameters for our neural network to learn. So let us see the different types, okay? So first, let us look at this general alignment. Okay. Notice that dot product or multiplicative is Q transpose K. Now, instead of Q transpose K, I have Q transpose WK. Okay. Q transpose WK. So let us now try and understand why is this W matrix coming here. Okay. Cool. If I'm taking an inner product, should the lengths be the same? Should the lengths of these vectors be same if I'm doing inner product? They have to be same, no? Yeah. If I put this W matrix in the middle, okay, imagine this. I have a K cross 1 Q vector. I have an N cross 1 K vector. If this W is K cross N, don't you think this whole thing will work? Okay, let me put it this way. Okay, let me put it this way. My key is N cross 1. My query is K cross 1, where K is not equal to N. If I now take a W matrix, which is a K cross N, I take this query vector and do its transpose, right? So Q transpose now will be 1 cross K, okay? And this key vector now is going to be N cross 1. Does this work now? It works, right? This works. So this is why we do this one. The general alignment function allows us to have different hidden state dimensions for my encoder and different hidden state dimensions for my decoder. This is the advantage of this general alignment function. Of course, how do we know what is the correct W matrix? We allow the network to figure it out. We set this as one of the trainable parameters and we let the network figure out what this W should be. Okay. So this is the first type of general alignment function. Let's look at the next one. Next one is additive alignment. Okay. So let's look at what additive alignment is. Sorry, no, this is different. Then, sorry, let's go to this one. The second one is bias general alignment. In bias general alignment, whatever I was doing with W, same thing now I'm going to do with an additional bias term over here, right? So I'm first going to do this W times Q thing first. I'm going to add a bias to it. And then I'm going to do the inner product of this vector with K, right? So all we are doing here is we're going from a dense state which has no bias to a dense state which has a bias. Okay, that's all it is. And finally, we have this activated general alignment where I take this bias general alignment and I simply put an activation function on it. Does this seem familiar? What these steps that we have taken, right? What is this called, by the way? First lecture of neural networks. What is this mathematical form called? What is this mathematical form called, guys? Isn't this a perceptron? Yes, this is perceptron. Okay, this is perceptron. So look at it this way. Before I was just using dot product. Now I'm using a perceptron. I'm using a perceptron there to learn what is the correct similarity to put over there. Okay, that is the idea behind this one. Let me quickly take Keshav's comment. As long as similarity was being calculated, it was fine. We were able to map and provide importance to where it was supposed to be. But won't W in general alignment functions misplace those mappings? Keshav, no. See, that is what, right? That is the advantage that neural network training gives us. It gives the network a chance to learn what is the best one. Okay. If the inner product itself is the best one, this W matrix will become the identity matrix. And this Q transpose WK will go down to Q transpose K if it is the best one. If it is not the best one, the neural network will figure out what is the best one and then give us an answer, right? So this allows us to let the neural network figure out what is the best energy function or energy score to put here. Do you now get it? Cool. Okay. So we want the network to learn something, right? We're giving it a chance to learn something here. That's the main idea. Fine. Now let's go to the additive alignment function. Okay. So guys, in some tasks, right, we will see which task specifically. We are going to discuss this task in BERT lecture. For some tasks, right, this energy score should not capture the similarity, but it should have something else. Okay. It should not capture the similarity, but it should capture some other aspect of similarity between these two, right? Something else. What that something else is, concrete examples we will see later. But now let us see how we can use this over here. So the major change now is instead of doing some operation between query and key, I'm using both of these as a concatenated thing. Okay. And I'm passing the concatenated vector through a neural network layer, right? I'm passing this concatenated network through a neural network layer. So essentially what I'm saying here is instead of fixing this to inner product, we will allow our network to figure out what this should be. So this is next level on top of what we saw here, Keshav. This is one level on top of that. Now we're even going to stop assuming that there is similarity. We're going to say, let the network only decide what to capture here. I have given up. I don't know what makes sense here. Let the network do it. So this is ways for me to do that. So now what I'm going to do is I'm going to take the key vector. I'm going to take the query vector. I'm going to pass it through a dense layer. Then I'm going to pass it through an activation. Then I'm again going to multiply it by a weight vector. This entire thing is known as the concat alignment function. right? This is what it is. Let me go back to Indradeep's question. So if we had two dense layers like W1Q and W2K, in the general form of the network would have learned better, right? Yes, Indradeep. But here is the thing, okay? Usually these key and value vectors are fixed globe vectors, right? So generally we don't want to apply anything on it before we pass it to this layer. So that is why we don't directly multiply it with W1 and W2. But you are right. When it comes to this, think of it as one part of this W matrix is multiplying this K, another part of this W matrix is multiplying this Q. So what you're saying makes sense in this alignment function. Cool? Yeah, yeah. Okay. So the intention here was we wanted to keep them separate, but now when we start using additive, we give up and this thing. A model inside model. Yeah. Hey, this is always the case, no? Even in computer vision, guys, we saw, no? If I increase the depth of my neural network, it improves. So model within a model, inception net, we have seen, man. So yeah, perfect. Good catch. Good catch. Good catch. Okay. So same thing is here, additive alignment. So over here, we are not concatenating these. Instead, we're multiplying them separately with these W1 and W2 vectors. We're adding them up and then adding a bias and then doing that. So actually, yeah, Indradeep, I just noticed what you had suggested before is this one, additive alignment. It's this one. Okay. And then we have this deep alignment. Okay. What is deep alignment? This is inception in the true sense. Why? Because now I have this EL, which is, think of it this way. The activated general assignment, the concat, and the additive, all three of these are single layers. This one is giving you the freedom to add 3 or 4 dense layers one after the other and then give it. So that is why this is deep alignment. Okay. So this is the third option. The final option for our alignment function is as follows. Our first one is convolution based and the second one is location based. Okay. So guys, this final one has a little bit of a nuance. This should be done only when you want to ignore keys and have it only depend on Q, right? So if you want to design an attention mechanism where you don't have a sequence to sequence task, right? Where you don't have hidden states from decoder. So you have certain neural network models which are encoder only or decoder only, okay? For such cases, for encoder only models or decoder only models, where we have a single RNN, in those cases, we have to use these alignment functions. My convolution based alignment function will come in when I don't have key and only have values. How am I going to do this? Okay. So first one is location based. Location based is simply going to be f of q comma k equal to E0, E1, so on till EDK. What is the meaning of this? It means that I have a single set of hidden states. Along with the hidden states, I'm going to give it certain numbers. These numbers will help my network identify which position this hidden state was in. I will concatenate these two and I will give the concatenated tuple as my output. So this is what I mean by location based. Okay, this is what I mean by location based. And convolution based basically means that I will construct my final output by doing a convolution operation on these key and query vectors or self convolution of this key and query, right? So this is what convolution based means, right? Okay. So this covers the 4 different types of alignment functions that I can design. Okay, cool. Is everyone with me so far? We have now discussed how to pick this one. We have answered this question, how to choose energy scores and attention weights. This, okay. Notice one thing though, I have not told you any other way of doing attention weights, right? Most often, guys, nobody replaces softmax. At least to my best knowledge, nobody uses something other than softmax for this. So everyone uses softmax to get attention weights from energy scores. So that part is going to be fixed. Okay, cool. Now let us see what are different types of attention mechanisms over here, right? What are different types of attention mechanisms? Now, let me explain what this is first. What I'm going to be discussing now is what can I change in my pipeline itself. So far, we have seen a fixed pipeline, right? We have only seen 6 steps. Now we're going to ask, can we change this so that performance increases? Okay, can we change this pipeline so that performance increases? That is what we're going to see. So let's see that. So different attention mechanisms. So first of all, have you guys come across these different terms like self-attention, multi-head attention, single-head attention? Have you at least heard this somewhere? Okay, some people have not, right? Okay, so people who have not heard these terms, guys, these terms are there left, right, center in any of these chat GPT papers. If you just pick one of those papers at random now, you will see this multi-head attention, self-attention. These terms you will see a lot. Yeah, attention is all you need paper is what you should check, guys. So the people who have not heard this, right? I want you guys to check one paper out. Attention is all you need. Yeah. This paper, try going through this. I'll just show you what I mean, okay? This is, by the way, the first transformer paper. So whatever I'm going to teach you from transformers point of view is going to come from this paper, right? I'll quickly show you where I want you to read. Like, I just want you to read one or two figures, just focus there. I'll show you that and then I will move on, right? Okay. And what we're going to discuss next is basically those different types. Now, this is in preparation for the transformers lecture, okay? If we understand it here itself, then we will be able to apply it for transformers. So, okay, I'll just wait for this paper to generate. In the meantime, I'll quickly discuss an overview of what these different types are. The first one is dependent on the number of sequences, right? Yeah. 74,101 citations, great. Yeah. You will see that this is the work which led to ChatGPT. If these people were not there, you wouldn't have ChatGPT today. Okay, so this is very, very important as a paper. So if you have to read just one paper in your life, right? Read this one. It came out in December 2017. So almost 18, yes. So I just want to take you here. Okay. So if you look at this paper, right, you'll see these different words: multi-head attention, masked multi-head attention, all that. So now we're going to try and understand what these things mean. Okay, we're going to try and understand this now. So let's focus here. Okay, cool. I'll put the link to this paper here. Oh, sorry, Command C. I'll just put the link here. If you want to read just one paper in your life, guys, please read this. Okay, it's a very well written paper. Means it is not confusing. They've not used too many jargon terms. So yeah. Okay, coming back. Briefly, attention mechanisms can be put into four categories: number of sequences, number of positions, abstraction, and representation. What does this mean? Let's understand one by one. So, can you guys tell me number of sequences, right? For this problem of aspect-based sentiment analysis, how many sequences do I have? One or two? One is the sentence itself, right? One is the sentence itself. Tell me, are the queries coming from the sentence or are they coming from somewhere else? Queries are coming from somewhere else, no, Arun? So we have two sequences here. One is the input sequence, the other is the query sequence. Okay. So based on this, so what I mean by number of sequences over here is to solve my problem, how many different sequences do I have to see? Okay. So based on this, we can have distinctive attention or we can have self-attention. Self-attention comes when you have only one sequence. Distinctive attention comes when you have two or more sequences. Exactly what this means, we're going to see shortly. Okay. Then you have number of abstractions. Okay. So number of abstractions basically tells me, am I focusing on the words or am I focusing on the sentences? So Keshav, this is where you have to come in. Okay. Keshav, you suggested something for one other task, right? What was the suggestion? Just want to go up and see that suggestion. Question answering, right? Question answering. Yes. So he made two things, Arun. He talked about translation and he talked about question answering. Okay. So in the question answering problem, do you think it's enough to focus on words or should we focus on sentence level? Sentence level, right? Sentence level. So the meaning of this number of abstractions is now we will have one attention mechanism to focus on the words. We will have a different attention mechanism which will focus on the sentences. So that is what we mean by number of abstractions. Okay. Now let's say number of positions. Number of positions basically means um, how am I making use of the, yeah, how am I making use of the probabilities that I'm getting from this attention weights? So far, we have just seen that we'll multiply this directly, but actually we have another option. We can do something apart from directly multiplying this. We will see there. Okay. So number of positions basically mean, should I change this or should I not change this? So we'll see this. And finally, we have number of representations. Okay. So over here, how many context vectors am I generating? How many context vectors am I generating? One, right? No. Indradeep, I'm generating only one here. I'm only having one context vector. So sorry, my bad. You're right in a sense. If I have 8 hidden states in the decoder, then I will have 8 context vectors. Yes, you're right in that sense. But per word, so per equation over here, right? In this output function, how many context vectors am I using? That was my question. In the output function, I'm using only one context vector, right? So now the basic meaning of this multi-head attention is, just like I have one thing to generate one context vector, I can simply put 5 or 10 of them there, right? I can simply put 5, 10 of them there. So if I start putting 5, 10 of them there, that is multi-head attention. That's all. Okay, that's all it is. Cool. Awesome. So Indradeep, I just want to address one question you asked me before. Hierarchy, yes. Number of abstractions determines the hierarchy. It puts the attention mechanisms in a hierarchical structure. Yes. And this is also multi-head. Yes, Arun. This is also a multi-head. So multi-head can come from having multiple similar units together or different units depth-wise. Both. Oh, again multi-head, repeat multi-head. Okay. So, to repeat multi-head, I just want to take you back. Do you guys remember our inception net? In inception net, if you remember, the problem we were trying to solve is we didn't know whether to choose 3 cross 3, 5 cross 5, 8 cross 8. What did inception net do? Use all of them, right? So the meaning of multi-headed attention is, now I don't know whether to use just this inner product or some other mechanism, right? So basically, multi-headed attention means I will have multiple different versions. I will pass my input through all of them, and whatever output I'm getting from all these attention mechanisms, right? The outputs I will get is the context vectors. So think of it this way. Instead of having just one context vector, I have 5 or 10 different context vectors. Is that now clear? Arun? Okay, I'll repeat. I realized I took this in multiple places. I'll just repeat once more. Instead of having just one context vector, right? If there is a complicated question which requires me to pay attention to both, right? Price as well as food. So if I now ask you a question related to both food and price, if I ask you a question like, is the food good enough to justify the price, right? You'll have to pay attention to both of these. So there I will require one context vector from price, one context vector from food. So multi-headed attention means I'm going to create multiple different energy scores, multiple different attention weights, and I'm going to create different context vectors from different attention weights. That's what it means. Yes, Arun, exactly. It's like different architecture of context vector generators to cover all bases. Perfect. That is the intuition of multi-headed attention. Okay, that's it. Indradeep says, so each attention layer in multi-head attention will generate one context vector. Yes, Indradeep, you're right. All of these are trained separately. Yes, all of these will be trained separately. Yes. Cool. All right. So let's go back. Let's go back to this. Let's quickly run through these now. Each of these in detail, slight detail. And once we do that, I will talk about, just 1 minute. I just want to see how much content is left for today. Yeah, we're going to see one example of multi-headed attention and we'll stop the class there. Guys, I don't think I have enough time to cover the code also today. So let's do one thing. We will see the code of this attention mechanism and this attention mechanism together. Okay, we will see both those codes together. So that's what. I have actually explained a lot of concepts from the Transformers lecture today. So that is why it's a bit like mixed up. But Yeah, let's do this now. Okay, so we have another 5-10 minutes remaining. In these 10 minutes, I just want to go over these different types. Okay, we'll see the details of these different types. We will see one concrete example of multi-head attention, and we will end the lecture. Is that okay with everyone? I might require 10 minutes extra. Is that okay? Okay, cool. Awesome. Thank you so much. Let's continue this. Okay, let's continue this. So now we're looking at what are different attention mechanisms. So quickly, what are attention mechanisms based on number of sequences? Okay. So first we have distinctive attention mechanisms. Okay. So guys, in distinctive attention mechanisms, the key vector is exactly equal to the value vector. Okay. So what does this mean? It means that okay, let's go back to this part. The textbook where I'm storing my information and the textbook which I'm using to generate the output are both the same. This is what distinctive attention means. But these two things are not similar to the query vector, right? They're very different from the query vector. So when I have the same textbook encoding my keys and values, but I have query vectors coming from somewhere else, this is known as distinctive attention mechanism. Can you guys quickly tell me for the task of aspect-based sentiment analysis, which do I use distinctive? Yes or no? Am I not doing this? Aren't my query vectors coming from the this thing? Yes. Okay, perfect. Just wanted to point that out. Fine. Now, this guys is essentially the same thing. This is like a computational chart. I don't want to go into the details because I've sort of explained this here, right? So I'm going to skip this part. If you guys have any doubts in this part, reach out to me. Okay. So I want you to sort of see this. This is nothing but how we'll exactly compute it. Now we'll go to the second part, which is self-attention. So we have distinctive attention and we have self-attention. So the meaning of self-attention is I'm now going to set the query as all the vectors in my key and value. Okay. I'm going to calculate an attention context. I'm going to capture one context for every sentence for every word in my sentence. This is what self-attention means. So this is like a greedy approach. I don't want to focus on one word. I want to focus on all of them and I want to create context vectors for all of them. Right? Does this make sense? Self-attention? Here, okay, let me repeat this. In self-attention, okay, and I'll give you an example, okay? So for question answering based tasks, right? There my query vector is different. Hold on. My query key and value are the same, right? What kind of summarization? Let's look at text summarization. In text summarization, do I know in advance what will matter and what won't matter? Do I know it in advance? Not really, right? I don't really know in advance what is important, what is not. Until I've seen the entire text, I will not know what is important, what is not. So I will get greedy now. In my text summarization task, I will create a context vector for every input, right? I will create a context vector for every token here. And then I will finally let my output mechanism decide which one to keep, which one to not keep. Is that making sense now? So we will use self-attention for summarization tasks. Okay, cool. In fact, we will use self-attention for this one also. So we'll see self-attention in a lot of places, guys. Think of self-attention as a greedy way. It's a greedy way of creating these context vectors. I will think everything is important and I will say all of these I'm going to take. Okay, that is what this is. Okay, now let's move on. What is attention mechanism based on number of position? Okay, so guys, this attention mechanism basically affects how we are calculating this attention weight, okay, and how we are calculating this context vector. It's basically over here. So it is going to affect these two steps. So let's see. So soft attention mechanism is exactly what I taught you just now. Okay, what is soft attention? In soft attention mechanism, my context vector is nothing but a weighted sum, right? It is a weighted sum of my value vectors, right? So soft attention is exactly what we learned just now. Hard attention, okay, is trying to solve a couple of problems with the soft attention. First of all, guys, can you tell me if my sentence is very long, don't you think calculating this context vector will be very expensive? Don't you think this will be very expensive? I have to think of so many weights, so many vectors. Oh, some people say no. Why? Guys, think of it this way. For a 10 length sentence, only 10 things appear in this summation. Oh, misclicked. Okay, that's fine. For a 10 length sentence, only 10 things will appear here. For a 100 length sentence, 100 things will appear here. So this is a big O of n operation. Okay. If this is a big O of n operation, maybe for large text tasks, this will be very, very difficult to manage. So one way to optimize this is, instead of saying my context vector is a linear combination of all the value vectors, right? Instead of this, can I not just pick the maximum one? So what I'm going to do now is, I'm going to take this attention weight. Okay, I'm going to take that. I'm going to find the maximum probability over there. And I'm going to say the maximum probability vector is my context vector. Make sense? Make sense? So instead of taking a weighted sum of all my value vectors, instead of taking a weighted sum over here, I'm going to take just one out of them and I'm going to return that. That is hard attention. So soft attention means linear combination. Hard attention means sum of everything, maximum one. Maximum one. Arun says, again, it depends on the application context, I feel. Yes, Arun, it does depend on application context. But here is the thing, okay? In a lot of times, right, even in the industry, speed matters more than accuracy. So this is one of those things which help you do the trade-off between speed and accuracy. This will result in less accuracy, but it will give you higher speeds, okay? So in a lot of places, you will see this being used just for efficiency. Okay, that's all. Cool. Now let's move on. What are attention mechanisms based on number of abstractions? So single level is what we have studied just now. Whatever we did just now is single level. Multi-level is exactly what I told you before. Okay, let's look at this diagram to understand multi-level. Okay, so I have my text here, the molecular basis of Rieger syndrome. I'm first going to encode every word as a vector. Okay, this every word as a vector I'm going to encode. I'm going to pass it through an attention layer over here, and this word level attention I'm going to pass to this. So this, I'm getting one context vector out of here, right? I'm getting one context vector out of this. I'm going to pass this as the encoding for my sentence. So this context vector attention output is going to be now a sentence level encoding, and I'm going to have another attention layer on top of this one. So do you guys see the hierarchical structure here? I'm first doing word encodings, then I'm doing sentence encodings. The sentence encoding is nothing but the output of the word encoding. Okay. This gives me a hierarchical attention mechanism. Okay, cool. Arun, I didn't understand your local question. Can we revisit that later? Just make sure you ask me later. For now, I just want to cover this, right? Okay. Now, finally, we have attention mechanisms based on number of representations, right? This is exactly what I was talking about before. Normally, what would you do? You would have query key value and you will give it to a single dot product attention, right? Now what I'm going to do is I'm going to give one to scale dot product attention. I'm going to give one to a neural network layer. I'm going to give one to some other thing. So I'm going to merge different strategies that we discussed for these alignment functions, right? We're going to use different alignment functions in parallel. Okay, we're going to use different alignment functions in parallel to generate different context vectors. So this H1, H2, H3 are three different context vectors which are coming from different alignment functions here. Once I do this, I have multi-head attention. Simple. Okay, this is multi-head attention. Okay, and now for convenience, what we're going to do is we're going to quickly see one example of a multi-head attention implementation, and I will end the class here. Okay, so just please follow along with me through this code. Once we go through this, we will end the class. Okay, so last thing, we're just going to see how we can apply different alignment functions to get different attention context vectors. Okay, so the paragraph that I'm going to encode here is food quality was not good as it was not cooked properly. Okay, I'm going to do this. So first what I'm going to do is I'm going to tokenize it. So all I'm going to do is I'm going to split based on the space. I will get different tokens over here. My target is nothing but my paragraph. Okay. Now, then I'm going to do the word embedding. So I have glow vectors of I for I in para, for para in paragraph, right? So this is like a vector embedding of each word which is there in this sentence. Then I'm going to stack this by applying PCA on it. So this will give me the glow vectors are some 100, 200 dimensions. I don't want to keep all of them. I just want to keep 5. Okay. So I'm going to do PCA on it and I'm going to extract just the top 5 most important directions. Once I do that, I'm going to have word embedding of the query text, right? What is my query text over here? Wait, where is it? I for I in target. Okay. Target is paragraph. Okay. So I'm setting the target also to paragraph. So my query is nothing but my input sentence. Guys, what type of attention is this? If my query is the same as my key, if my query is the same as key, what is this? Self attention. Okay, cool, cool. Just okay, awesome. Everyone knows this. Cool. So let's go ahead. So now what I'm going to do is I'm going to do multi-headed self-attention. We're going to see how to do this calculation. Okay. First thing we're going to do is we're going to have different W's for each of them. Now, for the sake of simplicity, we have just fixed it all to 1. But imagine that if I had given this to random values, these will be different, right? So for the sake of convenience of explanation, we have set this to the same. If you guys want to play around with this, change this from np.ones to np.random. Okay, and then run these cells. So now I have these things. Okay, so WQ is nothing but all of these. These are ones basically. These are 5 cross 9 ones. These are essentially weights which I'm going to use to do my multi-headed attention. Okay, let's do this. So now when I'm doing multi-headed attention, first thing I have to do is say how many I want, right? So I'm going to put 3 over here and then I'm going to proceed. So now think of it this way. I have key, query and value sequence which are being passed to a linear layer. For us, this linear layer is nothing but the glow vectors, okay? This is not a trained linear vector, linear layer. It is a glow embedding. We're going to fix this. Then what we're going to do is we're going to give each of these, we're going to use these to create these matrices. Then we're going to use these matrices in different this thing, right? We're going to use this for different attention mechanisms. Okay, cool. So essentially what we're going to do is we're going to multiply this input embedding to WK. We're going to multiply it with WQ and we're going to multiply it with WV. Okay. Oh, my bad. In this example, this WK, WQ and WV are the linear layers. When we're doing the application for attention-based sentiment analysis, we will fix these to glow vectors. For this example, they're different. Okay, sorry, my bad. I made one tiny mistake here. These are linear layers which we have defined over here. These weight vectors is what we're going to use to calculate the outputs of this. So that is what we're saying here. My key vector is nothing but I take my input embedding and I pass it through WK. I take my query X again and I pass it through WQ. And I take my value and I pass it to WV. Right? This is what I'm doing for this part. Then what I'm going to do is I'm going to split this into number of heads. Why am I doing this part? Because I want to give each of these things to a different alignment function, right? I want to give each of these to a different alignment function. So I'm splitting these now. Once I split these, I will have my different matrices like this, right? So the 0th part will go to the 0th alignment function. The first part will go to the first alignment function. The second part will go to the second alignment function. Cool. So once I do this, I have my embeddings first. After I pass it through my linear layer, I will have my vectors now. Once I do this, I can actually pass it through different energy functions and I set it here. For simplicity of explanation, we're going to use the same energy function here, okay? For simplicity of explanation. So, right, this is not very useful. Practically speaking, you would want to put different ones. But for example, this is okay. So now what I'm going to do is I'm going to do dot product between my key and query matrix. Then I'm going to get my attention values by doing dot product by this. Okay. This is like a ad hoc way of replacing that. No, this is that under root D, right? So since my length is 5, I will do under root of 5 and I will do this dot product to get my attention values. Then to calculate the context vector, I will get the attention weights. How am I getting the attention weights? By softmaxing. Okay. Once I do this softmax, I'm going to concatenate the 3 context vectors. So see this now. I now have 3 different context vectors. Over here in this example, they're all the same values because we chose a single alignment function. In practice, we will use different alignment functions and we will get this. Okay. In practice, we will do different ones. And finally, the multi-headed context vector will be nothing but each of these attention weights multiplied by the value, right? Each of these attention weights multiplied by the value. So now the whole thing is shown over here. So you have your X, you pass it through 3 different layers. You get your your query, your key and your values. You pass it through a softmax operation and through this alignment function. And finally, you multiply it with the value to get the final Z. Okay, this is the computational aspect of this whole thing. Let us see this in application. Okay, so now let's look at the sentence. The animal didn't cross the street because it was too tired. Okay, what we are now doing is we are selecting one word. This word is our aspect. My aspect over here is this it underscore. So what this guy did here, what these guys did here is they used 8 different 1, 2, 3, 4, 5, 6, 7, 8. Yes, they used 8 different heads, attention heads. Okay, and let us see what all it paid attention to. So one of those 8 attention heads paid attention to animal. One of them paid attention to cross. Does this cross make sense, by the way? Does this make sense? Can you interpret cross as a noun? Can you interpret cross as a noun? No? Guys, what do Christians worship? Don't Christians worship the cross? Yeah, cross can be a noun. Okay, cross can be a noun. So that is why one attention head actually got confused here and thought this cross means that Christians cross. Okay, so this it is now associated with this cross. So you have one attention head which is saying it means animal, one attention head which says it means cross, one attention head which says it means treat, one attention head which says it means because, and then you have these other ones. The ones in green are the correct ones here. The ones in brown are the wrong ones. Okay. So this is the advantage of multi-headed attention. Multi-headed attention allows my model to think of all possibilities in my sentence for it. And then in the next step, it will pick the correct one here. Does that make sense? Isn't this awesome? Isn't this awesome? Isn't this giving us some insight as to how ChatGPT thinks about different parts in the input? So ChatGPT has some big knowledge base. Okay. ChatGPT uses attention to think of which part to focus on when giving an answer. So in some sense, attention gives us an interpretable way of understanding what did the model think, right? So if you guys are ever debugging a ChatGPT model as data scientists in your career, you can look at the attention layer. You can focus on the attention layer to see what went wrong with your model, right? Make sense? Make sense? Cool. Okay. So with that, guys, I'm done with the content for today. Really sorry, I took a little longer to explain this attention part. What we'll do is next class, we will see how to apply attention in code. Okay, so we're going to see how to code this up. Actually, we're going to see how to solve this problem, which is the aspect-based sentiment analysis. And next class, we'll also look at the machine translation problem. Okay, so on Monday, I will discuss both these problems with you. We will see how to use attention to solve both these problems, and we will then have enough content to start discussing BERT from the class after that. Okay, cool. So what I'm going to do now, guys, is I'm going to start the doubt session. I'm really sorry for taking 13 extra minutes of yours, but this was important, right? So I wanted to go as slow as possible. Hope you enjoyed the class. And yeah, okay. Now I'll take the questions. Anil's question is first. Will the interpretability be reasonable for complex attention models? Yes, Anil. Most of the times, people say that attention is quite interpretable. I have not actually seen the results of complex attention models, so I can't give you an answer right away, right? But I know one thing, the transformers basically use multi-headed self-attention. So this interpretation works for multi-headed self-attention, right? This interpretation, this diagram which I showed you here was for the multi-headed self-attention case, right? I'm doing self-attention. Why is this self-attention? Because see here, the query is the same as my input. Why is it multi-head? Because I have different attention heads here. So at least for multi-headed self-attention, you can apply this interpretation. So we can understand transformers if we just know this much. I'm not sure about other more complicated versions, but let's see it later. But this is good enough for transformers. So that's good, right? Okay, good. Okay, so now let me quickly answer the questions which have been asked here. The first one is Keshav's question. Keshav, I hope you're still here. Why have we chosen encoder and decoder architecture only for applying attention mechanism? Are there any other possibilities? Keshav, did I answer this question during class? I think I dealt with this, right? Is Keshav there? Yeah. Okay, so I answered this, right? I'll just mark this as answered. So I'll just repeat the answer for brevity. We have chosen encoder decoder only for it. So we can do other things with it. Right now, we are seeing why it was first designed. Okay. The idea of attention came to these people because they saw these problems. So what I was explaining today was how did the idea even come first? The idea came from looking at this issue with LSTM results. That is why we've only been looking at encoder decoder. Next class onwards, we will see what else we can do with it. Okay. Next question is by Arun. The project is still not postponed. Please update the timelines. So Arun, I actually shared this feedback with the team. They told me that the project deadline have been set keeping in mind those 4 days. So if I want to apply for more extension, right? Like they said, they will not consider it. I have requested from my side also. Let us see. So if it is accepted, so can you just remind me what is the current deadline? Is it this Sunday? What's the current deadline? Can you quickly remind me? It's this Sunday, right? Oh, it's tomorrow. Okay. Wait. So my team 13th, right? Yeah, 13th is tomorrow. My team basically told me that they accounted for it and then gave the deadline. I will just ask them once more. I will request the people who decide this. I will put this point forward that people are not able to complete. Can we give more extension? Let us see, right? I will try my best, but these days they're not encouraging these decisions. So I will try my best though, right? So really sorry. Like they told me that they've taken that into account and set it. I will just repeat. I will request them once more from my side. So yeah. Yeah, for first week it was blocked by some technical. We need 2 weeks usually, but technical error. Okay, I'll just make that request once more from my side. I will argue that point. Okay, so now let me answer Anil's question. Cosine similarity equal to 1 minus cosine distance, then cosine distance equal to 1 minus similarity. Would that be correct too? Yes, it can, right? You're simply taking that minus cosine distance to the other side. And you're bringing cosine similarity to this side. So as an equation, it is correct, right? So yeah, as an equation, it is correct. So yeah, the math, this thing. But in one question, it's marked wrong answer. Which question, Anil? I'll get it fixed. Which question? Oh, sorry. Hey, 1 minute. Anil, I just realized what the problem is. I'm sorry. I realized what the problem is. The problem is this, okay? If cosine, sorry, what is the question again? The problem with the cosine distance is it's between -1 and 1, right? What I said will work only if it is between 0 and 1. Hold on. My answer was wrong. Wait, I just realized what the problem is. Cosine similarity equal to 1 minus cosine distance. Okay, so then cosine distance equal to 1 minus cosine similarity. So what I'm doubting is this even true, right? It shouldn't be true. I'll tell you why. Uh, so let us just try and understand. If I have two vectors like this, right? Theta here is equal to 0 degrees. So my cos of theta is going to be 1. So cosine similarity is defined as basically the angle, right? Cos of the angle which is there. So cosine similarity's definition is clear. The value of this can be between -1 and 1. The problem with distance metrics, right, guys, is that distance metrics are only allowed to be between 0 to infinity. Okay, there is no concept of negative distance, right? So that is the major issue here. I cannot have cosine distance as 1 minus cosine similarity because this can be negative also, right? Can this be negative first of all? No, this can't be negative actually. If it's -1, it will be 2. If it is +1, it will be 1. If it is 0, it will be 1. For 1, it will be 0. No, 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 no. No, it actually satisfies the distance matrix requirements also. Okay, let me take a look at this question. Just 1 minute. No, no, no. Mathematically, it looks correct. I totally agree. Uh, Text representation, right? Just 1 minute. I'll open that lecture and I will see what the question is. Hey, which with text representation, right? Okay, let's go through this. First, I will give my answer. I will not look at the solution. First, I want to see this. So first of all, magnitude of vectors affects cosine similarity. This is false, right? Because it only measures the angles. Range of cosine similarity is between -1 and 1, and that of cosine distance is 0 to infinity. This is wrong because we just saw cosine distance is between 0 and 2, right? We just saw this. So this is also false. Cosine similarity is used to capture the relationship of the words within a corpus with other words. Cosine similarity is used to capture the relationship of the words within a corpus with other words. This is true. And cosine similarity equal to 1 minus cosine distance. This is also 1 minute. This is where it's weird, right? Just 1 minute. 1 minus cosine distance 2. Huh? No, this is also true actually. So I will actually agree with both these sentences. I'll try and understand why this is given as wrong now. Yeah. Hey guys, this is a typo. There's a problem with the question. I'll get it fixed. Both of these are true right now. This is true, okay? Mathematically, this is true. I totally agree with you. I will get this question fixed. There is a very weak justification in the solution. I think they did a typo somewhere. I think what they wanted this to be was 1 plus. I think if they put this as 1 plus, we're done. So yeah, I'll get this question fixed. I'm really sorry for this. Yeah. Okay. So I'll mark this as answered. Yeah. So Anil, actually, even I was confused. Okay, I thought this will not satisfy the distance metric wala thing, but it actually does satisfy because 1 minus -1 is 2. So the minimum value that this cosine distance can have is 0, and that is one of the fundamental requirements of distance metrics. The minimum value has to be 0; it cannot go negative. So I thought that was where the concept was wrong, but it's correct actually. So yeah. Okay, cool. So with that, guys, I'm done. I honestly hope you enjoyed today's lecture. I tried my best to make it as intuitive as possible. If you have any doubts, concerns, comments, please get back to me, right? Yeah. And if you like the class, please don't forget to rate. If you didn't like it, also rate and tell me what went wrong. It's perfectly fine. Okay. Good night and happy weekend. Is that okay? Like if I end the class? Actually, I'm not getting any answers from anyone. Have I put everyone to sleep? Okay, okay, okay. Cool, cool. I was just waiting for a response. Sorry. Yeah. Good night, guys.